But now this particular session is on the fireside chat on emerging designs driving the semiconductor demand. We have Professor Kamakoti, the director of IIT Madras, Chennai, and is indeed the R&D leader in processor design as India's chief RISC-V architect. And along with him, we have Professor Dave Patterson, Pardee Professor of Computer Science Emeritus at Berkeley. And Professor Dave is regarded as the father of computer architecture, and he, along with Professor John Hennessy of Stanford, wrote the most definitive book on computer architecture, and is also the inventor of RISC-V processor architecture. And now, for the next half an hour or so, this will be the fireside chat on this particular subject of emerging designs driving the semiconductor demand. And let's have the videos, please.
Dear friends, we have with us Professor Dave Patterson. Professor Patterson needs no introduction. He is one who made computer architecture and who wrote computer architecture. Every serious student of computer architecture globally must have studied at least one of his books. Thank you very much, Professor Patterson, for agreeing to be part of Semicon 2022, India's flagship international semiconductor electronics meet. Now, the topic thank you. The topic for today's discussion is emerging designs driving the semiconductor demand. So, as an initial discussion, in your decades of deep association with semiconductor electronics, we would benefit from your views on the changing landscape of electronic designs over decades, say in the 1990s to 2000, 2001 to 10, and 2011 to this. We would be very happy to listen to your views on it.
Okay, well, certainly the biggest change is the ending of Moore's Law. It was just for basically my whole career since I was a grad student, Moore's Law, up until basically about 2010, Moore's Law held, right? We could have twice as many transistors every year or two for decades. And so I always kind of marveled that how fortunate I was to be in the computer industry, where we have this amazingly fast-changing substrate to build computers out of, as opposed to, suppose we'd been in the television industry or something like that. It was very slow progress, how different it must feel. And for those who weren't active at that time, computers were improving so fast that people would throw away, at that time, it wasn't laptops, it'd be desktop computers, but that were perfect, there's nothing wrong with them, but that they were just 18 months old and they were jealous of their friend's computer because it was so much faster and they get their work done. So you had to buy, you wanted to get rid of that one. So the hardware was just being, the churn was tremendous. And now you imagine with a laptop, almost, I mean, I think I replaced my laptop when it breaks. I don't think of it as speed as being a differentiator in laptop. So it was just an amazing time that that's happened. That was certainly by far the biggest change. And so as Moore's Law started running out of steam, we had to come up with other things we could do rather than just having the world's, a uniprocessor, a single processor computer that was twice as fast every 18 months, which was fantastic for software people. They would just add more features to their software and just wait for the hardware to make it go fast. So they didn't have to rethink their application. It was just a kind of manna from heaven, just what they wanted. So that changed in the 2005, 2010, where the cores themselves couldn't go faster, but we could put a lot more cores on the chip. And so that was the switch from, single processor, single core to multi-core. And it wasn't done because we had a breakthrough in programming technology that made that easy to use. It was done because we didn't know what else to do in the hardware design. So I'd say in the next transition is probably, 10-ish years later, where we're kind of running out of things to do with cores. How many applications take advantage of many cores? And so we've shifted to this new stage of domain-specific architectures, that if you really want to have a giant gain in cost performance, that the way to do that is to design something that only does one domain really well. It's exceptional at that domain, but it doesn't have to do everything like general purpose microprocessors. So what that means is domain-specific architectures will help narrow pieces of the computing industry, where before, with Moore's Law, it was like the tide that lifted all boats. Everybody's programs got faster every 18 months, which was really fantastic, but we can't do that anymore, so it's going to take big changes for software and applications and expectations of people. Many programmers still believe Moore's Law. It must be true because it held for 40 years. It can't possibly be ending. You architects are wrong. Go back and give me a fast gene processor, but that's not an option. There's nothing to do about that.
Sure. Thank you. So you have been a very strong supporter of domain-specific architectures. What do you think would be the major domains that would come up here in the near future?
Well, the ones that, there's kind of, I think the two exciting pieces of the computing industry are kind of at the polar opposites, right? It's the cloud, and that's where I'm at Google. That's where I do a lot of work, is in the cloud. And the other one is at the edge, is where smartphones and embedded devices. Those are the two exciting spots there. And you can do domain-specific architectures in both pieces. Interestingly, both pieces care a lot about energy. Energy is really important for both the cloud and these battery-operated edge devices. And so there's benefits in the cloud of using the tremendous energy that's in a data center more efficiently, so get more cost performance by more performance per watt. And on the edge, because you typically are driven by battery life, you want to get the best value of battery life. So it makes sense to do specialization in both areas. Kind of interestingly, the domain-specific architecture is done earlier in the edge. So the modern cell phone with the systems on the chip has a wide variety of what we call intellectual property, or IP blocks. All kinds of gadgets are on there because they compete on when you buy a new smartphone, why are you buying it? Well, how much better is the camera? How much better does it play videos and things like that? And a way that they make better cameras and play better videos or play better music is to use custom blocks on that. So kind of the edge is ahead of the data center in terms of domain-specific architectures, but since we have no choice in the cloud, we're seeing domain-specific architecture starting to go there. You asked about what areas. The one that everybody talks about today is machine learning, specifically deep neural networking within machine learning. And so Google's been building hardware to accelerate deep neural networking part of machine learning for almost a decade, where we put custom chips and their domain-specific architectures for machine learning, and as well as many people, including Google and its Pixel 6 phone, have dedicated domain-specific architectures for machine learning in there. So that's the one that everybody knows about, and the reason it's been so popular is because this application of machine learning is relatively new, kind of also just about 10 years old, where it's been around forever, but it started having real significant gains about 10 years ago, which meant that there wasn't this huge legacy stack of software. It was kind of brand new, and it's also, the machine learning code isn't that big. It tends to be modest number of lines in these high-level languages like TensorFlow or PyTorch. So it's not lines of code. It's kind of greenfield. It's not brownfield. It's not like legacy code. And there's all this excitement about machine learning, and it's very compute intensive, so we need special processors. So that's kind of the poster child for domain-specific architectures. And I think it's been a major success. Going back further in history, we didn't think of it as it wasn't graphics processors, GPUs. They've been around for a longer time. Now, it wasn't that CPUs weren't getting any faster. It was that you could make graphics processing, printing pictures, so much faster with dedicated hardware that made sense to do. So graphics processors are a historical precedent of things being done. And what's happened more recently with the graphics processors because they have a lot of compute power, particularly floating point operations, and not very much silicon area. They first got kind of migrated from graphics into high performance computing, and then to the great fortune of the graphics processor companies about 10 years ago, people found it was kind of the best silicon to doing machine learning, which was very floating point intensive. And so to their great fortune, people have also been using GPUs for machine learning. But those are the two kind of most successful examples of domain-specific architectures.
So we come to one of our favorite topics, RISC-V. I'm very happy to tell you that India has started a digital RISC-V initiative, Digital India RISC-V initiative. We call it DIRP. It was announced a day before by the Honorable Minister. So we have been a great fan of RISC-V, and we've been implementing RISC-V here. So we just want to understand what was the prime motivation for the RISC-V effort which you led up, and specifically trying to make the ISA open source and also on a BSD type of license. So it will be very interesting to listen to that. Yes.
Yeah, I'll try and tell you the story. So it was certainly, my name is associated with it. I helped, but primarily Krista Asanovich is the main faculty member involved, and then two graduate students who I guess Krista and I supervised at the time, Andrew Waterman and Yunsup Lee. Those three deserve more of the credit. I think what happened is I told them a story that in the 1980s we did 3 generations of RISC projects, and I wished I'd called them, I guess we did 4 generations. I wished I'd call them RISC 1, RISC 2, RISC 3, RISC 4 in retrospect. That would have been a better marketing thing. And I said that, told them that story, and so when they revived RISC architectures and tried to do a brand new, really great RISC architecture in the 2010, so like 30 years later, they said, well, let's call it RISC-V. Right? It'll be built on that Berkeley legacy, and so I think it's called RISC-V. I'm getting a larger share than I deserve. But in 2010, we were starting a big major research project. It was funded by many companies, including Intel, around the parallel computing, around the shift from what I told you about, from single processors to multiprocessors. We had no choice to do it, and yet the software wasn't ready, and we were doing a research lab upon it. Well, part of that was to do computer architecture work, because we knew in 2010 that we're going to want to get into domain-specific accelerators. We knew that was going to be the future. So we were going to do architecture work, but we wanted to enhance it with domain-specific accelerators. So that was the plan. So we looked at the existing instruction sets, and the 2 obvious ones were Intel's and AMD's x86 architecture and the ARM architecture. These are the 2 obvious ones. Well, they're not very elegant architectures. They're popular, but they're not elegant. They're often very complicated. Lots of stuff that they don't need that's been included for historical reasons over time. But setting aside the aesthetics, even because they're very popular, so that would make sense for us to work on them. But we weren't allowed to. Proprietary, they're owned by Intel or AMD, or they're owned by ARM. And even at the time, the companies were very sensitive about anybody outside trying to use their architecture. Even though Intel sponsored our research, they wouldn't have let us do it. So we were forced to do something new, and I think we also thought those other architectures weren't a great foundation. So we decided, Krista and Andrew and Yunsup decided, well, let's do a brand new clean slate architecture. Let's not be left any baggage over. Now, kind of the Berkeley tradition is to build things and share them. It goes back to, as you said, the Berkeley software distribution, BSD Unix. It even goes beyond that. If you know electronic CAD, there's the SPICE program that was, back when programs were in punch cards. Berkeley's been distributing software. That's been our tradition, feeling that we could have bigger impact if we gave it away, and then, than if we started a company to sell it. That's kind of the Berkeley tradition. So we thought in 2010, naturally enough, we would make it open source, and what our target audience was, we thought, was people like us. Is if we were going to put all this effort into a brand new clean instruction set architecture, Well, this would be a great foundation not only for our research, but for, at Stanford and MIT and all other universities. That's what we were thinking. So we made it open source. So as it turned out, almost no universities were interested in it. So we worked on it for 3 or 4 years. It got a lot better. We were using it in our classes and courses. Yeah, but other universities, they wanted to have the real thing. They wanted to either work with ARM or Intel because it was commercially viable, and this was just this Berkeley thing. Well, then I think it was you specifically, and then some other companies said, well, we would really like to have an open instruction set that anybody could use around the world. That would be, for a lot of reasons, that would be attractive, and just not for our research, but for commercial reasons. You don't want to be vulnerable to somebody buying the instruction set, or and changing the instruction set, or getting new owners, or having the flexibility to expand it, which we were going to need. So I think foundations, set up a foundation to get it going and try and make it happen. What can we do to increase the chances that we really could have an open architecture that everybody could use? And that's the origin story of RISC-V.
Sure. It was fantastic, and I think we all enjoyed doing this project, and especially when the first silicon booted and we booted Linux on that, then we really understood how powerful this has become, and the extensibility, as you say, has been extremely phenomenally useful for customization to different needs. Thank you very much. Thank you, Christy, and thank you, Dave, for this.
Right. What it turned out was, because we thought it was possible to expand the instruction sets if we were careful.
Yes.
And what the conventional wisdom was for Intel and for ARM is they insisted not on a kind of compiler compatibility, but what we call binary compatibility. And what they were worried about was fragmentation, that some customers would have some, and so that would be, so they prohibited it. It was just,
Exactly.
Past had been binary incompatibility was the death of microprocessors. And so we, not only were we open, we, encouraged people to customize. So it was a very contrarian view of how instruction sets should be done. And here we are, I guess 12 years later. And people, like you said, the customization is very popular today.
Yes. So very interestingly, we also did, just for the fun of it, a decoder for the x86. The area consumed by the decoder was close to our 5-stage pipeline entire processor. So, so that was the very interesting observation.
Well, the other thing on that line is because there's a bunch of RISC processors. A few people have, x86 is very unusual, and that's really hard to do. But a lot of the RISC processors are similar. So people have built instruction decoders that can handle multiple instruction sets, presumably ARM or MIPS or besides the RISC-V one. And that's because there's the similarities in the general RISC designs, that's not impossible, right? That's something that people can do, and I think some people are doing right now.
Yes. So India has now announced a $10 billion semiconductor mission to encourage, chips to be done and to strive the semiconductor industry in India. And as you know, India has the largest consumer market. So what, in your opinion, could be the steps India as a country could take up to make this mission successful?
Well, so kind of starting at the bottom, the easiest case to make for RISC-V is in Internet of Things or embedded devices, low-cost devices. They are power sensitive. There's arguments about RISC-V being better in that space because of code density and the simplicity of the architecture and the subsetability that's very attractive for embedded. The fact that it's free, so that could bring the cost down. And the customization. A spot where customization really works well is when you have a dedicated application and you care about either cost or battery power or something like that. So it's just a perfect match. So that's a natural place. So I think the next step above that, in talking to you in the past, I think would be automotive. I think you have a automotive industry in India, that is targeted for the India market. You have more than 1 billion people, so that's a large market. And increasingly, the bill of materials of automobiles has a huge fraction of the semiconductors. And we've certainly seen right now, at least right now in the United States, the unavailability of chips is limiting the production of cars and has raised the price of cars, even used cars, by tens of thousands of dollars, just because, supply and demand. They can't supply enough cars and the reason they can't do that is they don't have enough chips to do that. Now, Tesla, which, has a very innovative software stack, and they're able to adapt. They're willing to rewrite their software to use different chips. So they've been able to be they could use, not like, General Motors have to get the right chip. Oh, this is the wrong chip. Well, let's just adapt our software to use it. So they've been more successful. But I think it could be a strategic advantage for a country to have its own chip supply for its automotive industry. And this could be helpful around the world. And I think RISC-V would be a good match. And what's nice about that, it's a step up in that the processors can be more powerful than they could be. They could use more power. That I think when I saw a survey of use of chips in the car, there were like 40 different applications, from as little as tail light control up until engine control, and there's huge ranges of performance you need between that. So I think that would be a great fit for India. We've talked a little bit about the cloud, but the cloud's kind of at the high end. The cloud is, there's, to build a good cloud data center, it's 50,000 servers, megawatts of things, and there's a lot of software that you have to be ported to RISC-V. I think certainly embedded, and I believe the automotive, the software lift will be less. And that would be, anyways, that would be a great way to get started. If you're doing great with embedded, and then you're able to migrate to automotive over the next few years, you'd be in really good shape. And then, you could think that would also give some time for the software to mature for the data center. And if you wanted to get into the data center after that, after a few years, that would make it, maybe RISC-V, the data center will seem much more plausible, more believable in 3 or 4 years.
On the tool front, Google is now talking about a completely open source CAD flow, and there is a Google eFabless that is coming up. What is, in your opinion, would be like RISC-V has created a change in the computer way we look at computer architectures? Will this create an impact, and how it will be useful to the startups, right? So
I think so back when we did the first generation of RISC-V things, we were using academic software. We were using open source software for most of what we did. Now that was fewer transistors, and the clock rates weren't as aggressive, and of course it was much larger geometries, so the electrical engineering challenges weren't as great. But we did everything with open source software. So I'm a big fan. The Google work is being led by Tim Ansel, so I'm a fan of open source ECAD. And I don't know if we know how viable it is compared to commercial CAD products, but I think it's a start. It at least lets students be able to, anywhere in the world, to try it. And there's nothing quite as exciting. I think when I got started in computer science, it was taking the first programming course, and you see software come alive. And that, once I did that, like, okay, this is what I want to do for the rest of my life. I think you can get that same kind of excitement by building a processor. You build a computer. So you design a computer yourself, the chip comes back, and you plug it in, and it runs software. You can get that same, wow, I could build cheat. So both of these are inspiring opportunities, and I think what Tim Ansel is helping pioneer is one of the key roadblocks, which is where you can't afford the $10 million ECAD software that the companies can. So how are we going to do this? So he's kind of resuscitating the open source ECAD software to make this more viable, which makes it more accessible to a lot of people and should be fantastic in the classroom. So I'm a big fan. This is going to take a while to do, but I think if we get started using it and could see how well it works. I think we could also imagine, in the past, universities are pretty good at software. So if we could see what was missing in Tim's work and what we need to add, we could do that. And then there's this, I mentioned before about machine learning. There's this exciting opportunity that maybe some of the things that has very complicated software to do that the ECAD industry is doing, using a great deal of, millions of lines of code. Maybe some of this work could be done with machine learning. And with machine learning, the model is it's small, like I said before, small numbers of lines of code and lots of data goes through it. So if that's true, if the missing pieces of software of ECAD, we could replace the millions of lines of code with machine learning. And as long as that's good enough, it doesn't have to be perfect. If it's good enough, that could be a huge boon for increasing the number of design. Exactly. So I think this is another exciting area there. I think people at Google have a paper about placing a route in nature, and that's well documented. Bill Daly, my friend who's the chief scientist at NVIDIA, he just gave a talk, and he talked about uses of machine learning and other pieces of design, I think, in customizing the ASIC cells and stuff like that. So we're starting to see some evidence of machine learning being used to help build computers, and presumably if we can use machine learning for those pieces, that'll make it both cheaper and easier to do so that more people can do it. So it's another exciting direction that's happening right now.
Right. So in this direction, one of the important things that come up, like how you started the clean slate RISC-V, I think there is also a clean slate development of the tools, because the traditional CAD tools have a legacy issue, right? They need to be supportive of this. And I think this clean slate approach can exploit modern architectures and modern techniques like machine learning.
The other thing is, and this is my point with my friends in ECAD, is they don't work that well. The very expensive CAD programs, there's not that many customers for it. So they charge a lot of money for not very many customers, but they don't, because there's not that many customers, they don't have to get all the bugs out. If you're giving them millions of dollars, they will send a software engineer over there to help your company use it, and they'll explain how to use it, and they'll fix the bugs and stuff like that. But even if you got it for free as a university, you can't get that kind of support. So it's even big places like Berkeley and MIT can get access to that software. It can be a very frustrating experience because it's not intended, it's not as well polished as a lot of the software you're used to. So, the advantage of its open source software, you can, fix the bugs yourself, and you can interact with the people. There's more people you can interact with. And, I think the standards would be higher of how it will work, or at least you wouldn't have to, be begging one of these companies to please answer your question. So I think there's, you have to be careful what you wish for, right? Oh, I wish I had this $10 million ECAD software. Well, that's not the easiest stuff to use. And if you got the software without the support, that could be a very frustrating experience. So I think this, if we get, universities building ECAD software in the, or just people building open source in the domain, that could actually be a quality improvement of what's going on. Maybe we won't be able to use this to design, the latest high-end Intel or ARM microprocessor, but there's, a whole lot of chips that aren't at that stage that would be very useful to do, and that, students could do in the classroom, that small companies could do for their novel ideas. So, again, a very exciting time to be working in architecture right now.
Sure. So thank you very much, Professor Patterson, for your time, and it is very exciting. And certainly we would like to have you in India at some point of time, once things,
If ever safe to travel again, that'll be something I'll think about. But I really enjoyed visiting, and I hope you have a great conference.
Thank you. Thank you very much. Thank you very much. Namaste.
All right. Bye-bye.
Bye.